everyone. In this mini lecture, we're going to look at the topic of special right triangles. So we've already covered right triangles in a previous lecture. So special right triangles for us will be the 45, 45, 90 triangle theorem. Alright, so here's where the angles are: 45 degrees, and 90 degrees. So here's what the theorem says for us, and I'll draw the picture too. So let's say we have the right triangle that looks something like this. We know it's a right triangle by this little square at the bottom. So we have one angle being 45 degrees and the other angle being 45, and then of course the 90-degree angle. So in a 45, 45, 90-degree triangle, both legs are congruent. So this leg is congruent, I'll just call it X, to this leg right there, I'll call that X. They're the exact same thing. They're congruent. And the length of the hypotenuse is going to be the square root of 2 times the length of a leg. So basically X times the square root of 2. So basically we're going to say whatever the leg is, so if the leg was 12, then the hypotenuse is 12 times the square root of 2. So this works for a triangle that is 45, 45, 90 degrees. And this theorem works for us each and every time. All right, so in our first example, we're given a right triangle. How do we know it's a right triangle? Because of that little box right there, right? So it says to find the value of each variable. So what kind of a triangle is it? It's a 45, 45, 90-degree triangle. So that's the theorem that we just covered. So it looks to me that they want us to find the value of h, which is the hypotenuse, and z, which is one of the legs. So if you recall from the theorem just a few moments ago, just rewind back if you don't remember, the hypotenuse, right, the hypotenuse h is the square root of 2 times one of the legs, according to the theorem. Well, one of the legs we know to be a 9, so we can say h is equal to the square root of 2 times 9, or I'll clean it up a little and just say h is equal to 9 times the square root of 2. Alright, writing it either way is fine, but usually we like to write the coefficient in front of the square root symbol. And then the other variable, z. Well, z is the other leg, and the theorem told us that for a 45, 45, 90-degree triangle, both legs are the same, so z is equal to 9 as well. So our next example says to find the value of each variable again. So we're looking for the value of x, which is the hypotenuse. The hypotenuse, remember, is always opposite the 90-degree angle. So we're looking for x, and then we're going to find the value of y. Well, y is the other leg. Well, it's a 45, 45, 90-degree triangle, so the theorem tells us that the two legs are the same. So that y value has to be 2 square root of 2 units, whatever the units are. So then we can go ahead and use that information and go ahead and figure out what the x is. Well, we know from the theorem that x, that hypotenuse, we said, is the square root of 2, always. It's always the square root of 2 times the leg, right, times one of the legs. So for a 45 degree, 90-degree triangle, it's always, the hypotenuse is always the square root of 2 times whatever one of the legs is. So for us, it looks like we're going to do square root of 2 times one of the legs. Well, we just said one of the legs is 2 square root of 2. So this takes us to multiplying radicals. So with radicals, you only can multiply what's underneath and maybe what's on the outside. This is like saying 1 times the square root of 2 times 2 times the square root of 2. So that invisible 1 that's in front of that first one times this 2 will get us a 2. And then the square root of 2 times square root of 2 is square root of 4. Right? So 2 times the square root of 4, well, that's a perfect square root. That's on our list of perfect square roots that we should have. So that'll be 2. And then 2 times 2 is 4. So x is equal to 4. That's how much the hypotenuse is, 4 units. Alright, so moving into the next theorem for right triangles, it's called the 30, 60, 90 triangle theorem. So the angles are 30 degrees, which we have one right here. Next angle will be a 60-degree angle. And then, of course, the last one will be a 90-degree angle, and that's denoted by this little square in the corner. So this is another special type of triangle, 30-degree, 60-degree, 90-degree triangle. So for a 30, 60, 90-degree triangle, here are the characteristics. We have the smallest side, we'll call x, and then we have the other side, the other leg is larger than that smaller side, we'll call x times the square root of 3. The length of this longer leg is always the square root of 3 times the shorter leg. So basically, if I'm saying this shorter leg maybe would be 10, then this longer leg is 10 times the square root of 3. So we're always using the square root of 3. And then the hypotenuse, the longest side, the side that's always opposite the 90-degree angle, this is always twice the length of the shorter leg. So again, for example, if the shorter leg were 10, then the hypotenuse is 2 times 10, which is 20. So these are the characteristics for this. Alright, so this example says to find the value of d in simplest form. So here we're given a 30, 60, 90-degree triangle. Right? We see the 30 degrees, 60 degrees, and then the little square indicates that's 90 degrees. So it's the 30, 60, 90-degree triangle. We're given that the shorter leg is d, unknown. The longer leg is 5 units. And the hypotenuse, the leg, or the side, I'm sorry, that's opposite of the right angle is f, which is also unknown. But some important information that we have is written here in this bubble. The hypotenuse is equal to the square root of 2 times the shorter leg, and the longer leg is always equal to the square root of 3 times the shorter leg. Now this is the information that we just spoke about in looking at the theorem. I've just written it out for us to have. So make note of that. That's so very important. So we're going to use the longer leg to help us find that shorter leg, that unknown, that d value, right? That shorter leg is d. We know that the longer leg is the square root of 3, times the shorter leg. So the longer leg is given already as 5, and that's equal to the square root of 3 times the shorter leg. The shorter leg is d. Let's go ahead and rewrite it in a way that it's a little bit more clean. This is fine, but usually we like to write a coefficient or variable in front of the radical. So we'll say d times the square root of 3. So 5 equals d times the square root of 3. Now looking at this, you have to perform a little bit of algebra, but don't let the square root symbol trip you up, right? Between d and the square root of 3 is multiplication. So just think back in algebra and say, okay, how would I solve for d? Well, this is multiplication, so you do the opposite, which is division. What you do to one side, you do to the other side. So you're dividing both sides by the square root of 3, right? So when you divide both sides by the square root of 3, they both cancel out. You're left with d is equal to 5 over the square root of 3. So there's a little thing in algebra where you cannot have a radical in the denominator, right? If we have 5 over the square root of 3, we need to do what's called rationalize the denominator, right? We can't have the radical in the denominator. If we didn't have a radical there, then we would probably stop and say, okay, it's 5 over or whatever. But we can't have that, so we do what's called rationalize the denominator. So what we do, we take the denominator and multiply it by the top and the bottom. So 5 times the square root of 3 is 5 square root of 3. The square root of 3 times the square root of 3 is the square root of 9. Well, what does that give us? 5 square root of 3 over the square root of 9 is 3. So this is what D is for us. D is 5 square root of 3 over 3. And this is fine because now there's no radical symbol in the denominator. This is the exact value. You could actually put this in your calculator and say 5 times the square root of 3 divided by 3, and then you would get some decimal, but that's just an approximation. We want exact values unless we ask for an approximation. So this would be our final answer for D.